Okay. Again, a little sound check. Sound check, sound check. Sound check. I'm gonna set a time for tonight, but to be honest, I don't know if I'm gonna last 2.5 hours because I'm feeling pretty rough today. So it might be we cut this one short, or we stop at a natural stopping point. Right, let's see where Twitter's at. Twitch. Go on, wake up Twitch. Heyo. Actually, someone watching on Twitch for about the first time in a long time. Action. Let's go. How do I like reply to that? No, my keyboard's away from that. What time is it now? Twitch should be 1 more minute and it should be coming up. Twitter's thing, so how long have I been coding? Good question. Since I was hold on. I guess including university, but I guess from work since I was 21. So how many years is that now? 13 years. 13 years. Yeah, Twitter's finally played catch up now. Huzzah. Started your journey during the pandemic, yeah. I think a lot of people did. How you found it so far? What do you sort of like? Do you specialize in anything? I'm guessing do you have a role in tech now, software engineer, or? Looking for work. Yeah, marketplace is it's pretty rough right now, so I don't envy you. Operations is my friction point. Okay, we're all up and running now, so I think we might as well just get started. Right, let's get this on. Okie dokie. So today, yeah, you can only grind. That's the lever in my control. Yeah. If you're looking for work at the minute, I'd say definitely be working on projects and especially things that you can get usage behind. So either like a SaaS or an open source project that'll actually people actually find useful to use and stuff. I could really recommend that. That is the way sort of like people will be able to sort of differentiate now, or start some content as well, like start sharing what you're learning on the minute, what you're grinding on. So like spent 30 days doing X, Y, or Z, whatever it might be. Playing with LLM deployment and monitoring. Plan to blog about it in September. Yeah, absolutely. And I'd say get out into wherever it is that you live. If there's communities in tech around there, definitely get out and speak to people and meet people in person and stuff, because that is another big differentiator. Is getting out and actually seeing people in person, because everything's going very very kind of digital and just noisy with AI, obviously creating content and all sorts of things and stuff. So best to you. PyTorch basic and some terminal training. Yeah, just write about it, share it. You don't need to be an expert. Just share with the world. But cool. Well, I hope you get something out of tonight. I'm going to be starting on, and to be honest, it might just be one chapter because there's 23 lessons. I'm completely new to C, so I have no idea how this is going to be. Depending on how thingy this is, it might be we get through just one chapter, it might get through a few. I'm going to try hang in there because I'm not feeling like too great today, but I'll at least try and get through one chapter, because this is a bulky one, and the next courses after this one, we completed 10 so far, ignoring the AI one because that was added in like after I already started the path. And I don't know why there was like 4 lessons after that, because I completed it. Maybe again it was another thing that was added afterwards, but we're going to make sure we get through all this stuff as well. So yeah, we'll focus. Let's get started. Yeah. So, welcome to memory management. Understanding how software runs on hardware is important for writing fast, performant code. In this course, we'll be talking all about one of the main aspects of software performance, memory management. So, and this chapter is just all about basics of C. Okay, cool. So let's get started.
Hi everybody, my name is TJ and I will be the host of Introduction to Memory Management, a course that is going to give you, the student, an overview of what it means to manually manage memory, which is different than all of the languages that you've encountered so far on Boot.dev. And as we learn more about this, we're actually going to work our way all the way to building 2 simple versions of garbage collection. Now, if you're not familiar with what garbage collection is, you might first assume that it's the thing that comes and deletes all of your coworkers' code. While that would be a useful feature for any language to have, that's not actually what we're going to build in this course. Instead, we're going to build something on top of a simple object system that we learned to build, how to either track objects directly and find when they're not referenced, or using an alternative approach called mark and sweep, we'll be able to find out if any of those objects are still alive. Now, that might sound complicated, but we're going to take step by step along the way. We'll teach you every C feature that you need to know to be able to build this. And then as we progress through, you'll be exposed to more and more ideas about manually managing memory in C, as well as how other languages manage memory for you. I hope you really enjoy this course, and I'm looking forward to all of you coming out on the other side with a better understanding of how your languages work, what happens when your computer grabs and releases memory, and ultimately coming out with more skills and language to be able to talk about the kinds of problems that you're going to encounter as a backend developer. Thanks everyone, and I'll see you in the next lesson.
Sounds good. So, goals of this course. So, understand how and where programs store data in memory. Variables, functions, and objects don't get to exist for free. Where do they live as your code runs? Learn how to make programs more efficient, so most performance-related problems in back-end software are memory-related, at least in my experience. Learn how it all works so you can troubleshoot and optimize. Practice programming in a lower-level language. C gets you much closer to the hardware than Python, JavaScript, or Go. By writing C, you'll learn a lot about how software works closer to the metal. Learn about garbage collection and build your own. You will likely work in a garbage collected language at some point, whether that's Python, Go, JavaScript, or something else. Best to understand what trade-offs are being made. This is not a C course. We will be writing C code, and we'll cover the basics of C that you'll need, but we're focused on our memory, not C. Okay, that's fair enough. So prerequisites, coding experience. You should be comfortable writing code in at least one other language like Python, JavaScript, or Go. CS basics. We expect that you understand basic algorithms, data structures, object-oriented programming, functional programming concepts. Building Schnecklang. If you're familiar with super high-level languages, you're probably not used to not thinking about memory. In this course, we'll be building the Schnecklang programming language. Okay, just little parts of it in C. We will study all about manually managing memory in C, and toward the end of the course, we'll build a simple garbage collector so that Schnecklang devs don't have to think too hard. A small bit of irony here is that C was originally considered a high-level language when it was released, and in fact, in some ways, it still is. Modern compilers and hardware are incredibly cool and make impressive optimizations. But even so, I think there are a lot we can learn on our Schnecklang journey. So, assignment. The ultimate crime has been committed. Someone confused Python with Schnecklang. Update the code to print, starting the Schnecklang interpreter. Make sure to keep the /new line character at the end of the print statement. So, oh, failed the first one. Schnecklang. What's up, my mouse? Oh. Yay. Whoops. Okay, it's a little bit. Ta-da! Oh, a little bit slow today. Right, come on then. Easy peasy. So, C program structure.
Now you're probably wondering, okay, so we're going to learn about memory. How are we going to do that? Well, we're going to use C as a vehicle for that understanding. This course isn't primarily motivated as the best way to learn C. Instead, we're going to use C as a way to express ourselves to the computer about what we wanted to do with memory. Now, I don't want you to be worried. We're going to start all the way from how do I get my very first C program to run and take you step by step from there all the way up to using structs, enums, unions, a little bit of macros, all along the way so that you can have a strong understanding of the language before we start implementing more difficult aspects like our own little object system, a ref counting garbage collector, and a mark and sweep garbage collector. There are a few things that we won't be covering in the course, like we won't be covering different build tools, versions of C, or random foot guns that you encounter once your C project gets past 1 million lines. That's not the main focus of the course. Instead, we're trying to give you the tools and the language to understand what's going on when you're running code on the computer or when your garbage collector runs, when you're using some language like Python, Go, or JavaScript. With all that being said, let's go make our first C program, which is just going to do the classic printing something out to the console.
Okay, so in Python, you do something like this. Python slow program.py. The Python interpreter then executes the file top to bottom. If you have a print at the top level, then it will print something. The entire file is interpreted line by line, but that's not how C works. So the simplest C program. The simplest C program is essentially int main function return 0. But a lot's happening here. A function named main is always the entry point to a C program, unlike Python, which enters at the top of the file. Int is the return type of the function and is short for integer, because this is the main function. The return value is the exit code of the program. 0 means success. Anything else means failure. You'll find a lot of abbreviations in C because 1, programmers are lazy, and 2, it used to matter how many bytes your source code was. The opening bracket is the start of the function's body. C ignores white space, so indentation is just for style, not for syntax. Return 0 returns 0. The 0 value, an integer from the function. Again, this is the exit code because it's the main function. 0 represents nothing bad happened as a return value. The pesky semicolon at the end of the return 0 is required in C to terminate statements. The closing bracket denotes the end of the function's body. So print, it feels very different coming from Python, but printing in C is done with a function called printf from the standard input output, I don't know what the .h means, standard input output library with a lot of weird formatting rules. To use it, you'll need to have an include at the top of your file. Then use the printf from inside a function. Notice the /n is required to print a new line character and flush the buffer in the browser, which print in Python does automatically. In case you're wondering, the F in printf stands for print formatted. Assignment: create a small C program that prints program in C. So we'll have I guess is it string main, and then but we'll change that to program in C. Oops. And then to test that, control enter. Oh, wrong. So I can't do string, can I not? Int. Oh, I suppose like I have to still return 0. Okay, is that the thing? 0. Happy days. So the main function always has to return 0. Okay. 0 means 0 error from the command, I guess. Yeah, makes sense. Interpreted quiz. Up until now, you've probably only worked with interpreted languages on boot.dev. Use the following interpreted, in this case Python, code to answer the question. Print starting function that doesn't exist. Print finished. Assume that function that doesn't exist is a function that truly does not exist. What will happen when the code runs? Okay, so Python, stack trace due to undefined function prints, starting prints, then a stack trace due to undefined function prints, starting prints, that one. Yeah, and we'll get it to explain it just in case, like, so it goes top to bottom, that's why it does the print, and then it can't do anything with the non-existent function, so then the stack trace is called. It's like a fly in here, can't quite get it. Yeah, so excellent question. Let me break down why starting prints and the stack trace due to undefined function prints is the correct answer. So in interpreted languages like Python, code is executed line by line as the interpreter reads it. Here's what happens step by step. Line 1, line 2, line 3. The interpreter executes print starting successfully, so starting gets printed to the console. The interpreter tries to execute this function. Since the function doesn't exist, Python raises a name error and the program crashes in stack trace, showing the error. Because the program crashed in line 2, the interpreter never reaches this one. Yeah. So the key characteristic of interpreted languages is they execute code sequentially and stop immediately when they encounter an error. The program doesn't get pre-checked for all possible errors before running like it would in a compiled language. So the output will look something like that. Yep. Okay, we're going through this pretty fast. Maybe we get through a few chapters tonight. C is compiled. The Python code prints starting before it crashes, but in C it crashes before it can even run. If there is a problem, the compiler tells us before the program even starts. Now, C doesn't tell us about all the possible problems, read skill issues, that might arise in our program, but it does tell us about some of them. Okay, let's listen to this 4 minutes. Okay, let's see.
If your only experience with a compiler is using the glorified linter, commonly known as TypeScript, then you're in for quite a treat here. We're going to be talking about some of the distinctions between interpreted languages and compiled languages. On the one hand, we have interpreted languages like Python or JavaScript. Examples of some compiled languages would be things like Go or Rust. C fits into that compiled language standard. The primary distinction for interpreted versus compiled, although this occasionally is a little bit blurry, is that interpreted languages have some sort of interpreter that runs and executes the code line by line. Now, that's not really true anymore. Computers are much more complicated than that, and we figured that running things line by line actually makes stuff really slow and bad. So lots of languages have things like just-in-time compilers, JITs. Let's leave those aside. We're going to talk more broadly in the sense that if you run Python and you're walking down the file and you run into a function that doesn't exist, that's when you're going to get the error. It won't happen when you first run Python my file. It will happen later. Compare this to compiled languages, which generally speaking have some sort of compiler that actually checks some sort of type system when they're done. That type system can range from incredibly elegant and beautiful, like OCaml, to simplistic and painful to work with, like Go. Shout out to Lane for this. Either way, the compiler is going to do some checks ahead of time, turn your source code into some sort of executable, and then allow you to run that executable directly. In general, compiled languages are a bit more performant than interpreted languages. Now, there's a huge range here. Some compiled languages are still very slow, and some interpreted languages have gotten very fast. It's not always that every piece of code written in a compiled language is going to be an interpreted one. However, generally speaking, you should be comfortable saying a compiled language probably faster than interpreted. As I mentioned previously, one of the other things that's quite nice is that a compiled language will let you know that there's an error at compile time rather than waiting until running into that problem during execution. Now, there's different classes of bugs that can be caught by compilers. You'll find that the C compiler often does not help you, but you'll find that the C compiler generally does help you with certain things like functions that don't exist, fields that don't exist, or variables that don't exist. It is able to catch those, and that is quite helpful during the development cycle. One of the other benefits of compiled languages is that, generally speaking, you can run or execute the binary without bringing the entire language to another computer. So, for example, when you download an executable from the internet, just any old website, just run it because it says .exe, what could go wrong? That's a compiled language building that so that it can be executed on another computer. As opposed to if you download a Python script, you're going to need Python on the host program to run that script. Some cons for compiled languages is that depending on the size of the project and the compiler itself, the compilation step, the part that takes your source code and turns it into something that can be executed, can take a long time. I know people for whom this XKCD meme of doing whatever they want while they're waiting for things to compile would be an acceptable behavior at work because they literally can't do anything until the compilation step is done, and it could take on the order of minutes or hours. The other con that defenders of interpreted languages will often make is that when you have a compiled language, you always have to fix all of the things the compiler is warning about before you're able to execute anything. This can be kind of annoying if you're trying to iteratively test some small thing and you know you're only going to run over this part of the code. You might not care that other parts of your product are now erroring. You just want to test this little block. And it is true that a compiled language will then just prevent that from happening. So there is something to be said about a rapid iteration speed that sometimes an interpreted language might make easier to do than something that's more statically typed and compiled.
Good assessment. Yeah, some good points on that. Assignment. Run the code noticing that starting message never prints. Fix the bug by removing the non-existent function call. So just run it, and then get rid of that. Yay, easy peasy. So comments. In C, there are two ways to write comments, a single line comment and a multi-line comment. I could just keep adding lines and it will still be a comment. Yeah, multi-line. So assignment. Looks like someone on the team doesn't know how to terminate a comment. Fix the bug. Yay. Basic type. So int, an integer, float, floating point number. Char, a character. Char, asterisk, an array of characters. More on this later. If you think about it, it sounds kind of like a string, doesn't it? You've already seen int in the example before. It's the return value in the special main function, the entry point for every C program. Assignment. Someone allowed a Pythonista into our beautiful C code base. Fix the bugs called by missing types on lines 4, 5, and 6. Fix the bugs caused by missing types on lines 4, 5, and 6. Oh, okay. So int like that, is it? Char, and then float, is it? Don't touch the line below this. Hooray! Max recursive calls, that. Input output mode, that. Got speed. Strings. Most programming languages these days, even compiled ones, have a built-in string type of some sort. C doesn't. Instead, C strings are just just arrays, like lists of characters. We'll talk more about specifics when we talk about arrays and pointers later. But for now, know that this is how you get a string in C. So char asterisk and then the thing, and then all that. I repeat, very loosely speaking, character asterisk means string. Also note that it is required to use double quotes, single quotes make char and not character string. So fix the bug on line 4. So car asterisk like that. Just going to go for it straight away. I'm confident. Okay, always has to have double quotes. Start with the type and the name, the variable. Printing variables. You've already seen me do a printf magic a few times. Unfortunately, in C, it isn't as easy to do string interpolation. What f strings do in Python instead. Instead of print f hello and all that, yeah, you have to tell C, we have to tell C how we want particular values to be printed using format specifiers. Common format specifiers are percentage D is a digit, percentage C is a character, percentage F is a floating point number, percentage S is a string, a character asterisk. So printf, yeah, that. Okay. Print new line character. The print function in Python automatically adds a new line character /n at the end of the string. In C, we have to do this manually. So assignment, in the space provided, print that stuff. Okay. Oh, I'm going to keep that. And then it's going to be print. Oh, do we have printf in a... Yeah. So it's going to be like that. Whoops. Default max threads. 1, 2, 3. Okay, so then A is going to be use format specifiers to replace A to D with already provided variables. So default max threads, so it's going to be digit, is it? Yep, digit. It's going to be snack lang. I don't want to type it all out. Snack lang default max threads. Custom perms, so like that's going to be I guess a character like that. This variable snacklang default pi is going to be a float, and then snacklang title is going to be a string %s like that. Yep, pretty simple. Compilation types. So you're probably familiar with the idea of types from Python, but C does them quite a bit differently. In Python, it's okay, but still disgusting to change the type of a variable. In C, changing the type of an existing variable is not allowed. Call bad cop, this is illegal. In it's okay to change the type of an existing variable. Python. Variables, as we talked about, variables cannot change types. However, a variable's value can change. Yeah, that's fine. Makes sense. Assignment. Run the code, you should get a compilation error. When updating a variable's value, you don't need to declare the type. In fact, you can't fix the code so that it updates 64 to 32 properly. So yeah, there's the error. Redefinition, yeah. Easy peasy. I quite like this so far. This is nice. Constants. So a variable value can change. But what if we want to create a value that can't change? We can use the const type qualifier, which properly declares a const in C. That one. Meaning life is 42, actually. So functions. In C, functions specify the types of their arguments and return value. So flow, add. Yeah, makes sense. First type, float is the return type. Add is the name of the function. Int y and int x and int y are the parameters to the function, and their types are specified. X plus y adds the two arguments together. Float casts the result to a float. We'll talk more about cast, what cast means later, and the rules for casting to and from certain types. The simple version is that it instructs C to treat the result of x plus y as a float. Here's how you would call this function. Yeah. So float result equals add, and then those two numbers, print the result, and then return. It's nice that C functions enforce returning the same type from all return statements, isn't it? In Python, it can be a pain to realize that a function returns different types depending on the path it took. Write a max snacklang memory function in the space provided it should accept two arguments. Oh. So int snacklang memory. So it should take 2 arguments, int max threads, and then int memory per thread. Return integer representing the total memory available to the snacklang interpreter. Okay, so that's going to be return. And then it did say, like, you know, in the example about that, it's have it as an int, but let's just do it with max threads times memory per thread. Let's see what it does. Maybe we have to cast it. Oh, yeah. Whoops. Used to not having to put semicolons. Now we need to put semicolons. Okay. Yay! So we don't have to cast it, but yeah. So void. In C, there's a special type for function signatures, void, where there are 2 primary ways you'll use void: to explicitly state that a function takes no arguments, when a function doesn't return anything. It's important to note that void in C is not like none in Python. It's not a value that can be assigned to a variable. It's just a way to say that a function doesn't return anything or doesn't take arguments, which is valid. Void x none, void SSH terminal shot, char string, string address, void print hello, void int get number, void. That one. Whoops. Oh, that one. No, this one. What? Hold on, let me refresh. That doesn't seem right. Oh, which is not valid. I'm dummy. I clicked all the valid ones and not the non-valid one. Whoops, I just lost my streak. Ah, well. Unit test. So up to this point, we've been checking the standard output of your code against our expected output. Now that you're familiar with functions, most of the lessons will be graded using unit tests. So, fancy looking thing. Unit. In particular, we'll be using unit or munit testing framework. It's simple, lightweight testing framework for C. So, run versus submit. Boot.dev, the run button is for debugging. The submit button mimics the idea of publishing your code for production use. You should be debugging your code using run button. You should be adding printf statements in your code to make sure it's doing what you think it's doing at different points in the code. Write a line to calculate a value. Write a line to calculate a value. Printf the value you calculated. Run the code. Did it print what you expected? If not, fix it. Repeat. You will never lose XP or be penalized on boot.dev for using the run button. However, there are consequences for submitting broken code, just like there are career consequences for pushing broken code to your users. Like how edge cases can creep upon you after shipping code to production, some test cases are only executed on submit. That's fine. We already know this from all the lessons we've had on boot.dev anyway and stuff, so that's fine. File layout. Let's take a look at main.c file. You'll notice it's read-only. You can't change tests that would make it too easy to cheat. It includes exercise.h at the top. Open exercise.h and you'll see the function prototype signature of the function you need to write in C. C contains .c files contain the implementation code. .h files are header files that contain the function prototypes. To import code from another file, you need to include the .h file. Exercise.c includes exercise.h. Main.c includes exercise.h. This allows main.c to call functions implemented in exercise.c. Write the getAverage mathematical average function in exercise.c based on the function prototype expected in exercise.ch. So I'm just going to get that. And we're going to do this. So we're already halfway there. Average. So it's going to be return. Do this. X times y times z divided by 3. Oh, semicolon. I'm going to take a while to get used to that. Oh, fail. Oops, I might be doing it wrong. Might be some. Sum them all up and then divide by how many there are. No? I have to cast it to a float. There we go. That was probably it. I was just checking that we're paying attention. Okay. Math operators. So, surprise, we got this far and we won't show math operators. We just kind of guessed it, but it is what it is, I guess. No probs. So math operators. So all the same operators you'd expect exist in C. So plus, minus, asterisk, and slash, divide. Plus, minus, time, multiply, divide. If you're coming from Python, plus equals, minus equals, asterisk equals, and slash equals are all the same. In addition, there are also plus plus and minus minus operators. The name of C++ is a bit of a joke by the creator. It's meant to be incremented C or better C. These increment double pluses and decrement double minuses operators can be used in two forms: postfix and prefix. Postfix is when you put them at the end. The value of x is used in that expression first, and then the x is incremented or decremented, for example. So a is equal 5, b is equal a plus plus. So b is assigned to 5, then a becomes 6. Okay. Prefix. So x is incremented or decremented first, and then the new value of x is used in the expression, for example. A becomes 6, then b is assigned to 6. Okay. Didn't realize that. The value of x is used in the expression first, then okay. I generally avoid prefix operators. If I want to increment a variable, but keep the original value, I do that in 2 steps. Postfix is more common, especially in loops, which we'll get to. So assignment: complete SNEC score function in exercise.c. SNEClang is unique in that its toolchain gives developers a project score that's dependent on how many maintainable and high quality their code base is. The larger the score, the harder it is to work in the project. The score is calculated as follows. So you multiply the number of files by the number of commits to get the size factor. So I'll say, I guess, multiple number of files by the number of commits. So it's going to be int, and it's going to be size underscore factor equals num files times by number of commits, num commits. Add the size factor to the number of contributors to get the complexity factor. So complexity score factor, and then size factor plus what was it? Number of contributors. Num contributors. Semicolon. Multiply the complexity factor by the average bug critically to get the final score. So I guess we'll just do return complexity factor times by see if that does it. Oh, semicolon. I'm going to keep doing that. Okay. Tip. You can convert an integer to a float by casting it. I don't really need that, do I? See if it passes. Hey. If statements. So, if statements are the most basic form of control flow in C, very similar to other languages. Basic syntax. If that, print then that. If else, else if are also available. So if else, yep, nice. Chunky syntax. If you can write an if statement without braces if you only have one statement in the body. But this shorthand is easy to mess up, and in my opinion isn't worth saving a couple of lines. There are enough ways to shoot yourself in the foot in C already. So assignment. Take a look at exercise.h. Write the implementation for the function prototype found there back in exercise.c. It should calculate whether it should calculate whether the given temperature is too cold or too hot. It's already in Fahrenheit, of course, the most reasonable scale for regular living. Less than 70 return too cold. More than 90 returns too hot, otherwise return just right. Do not add a / enter the beginning of the strings. That's done at print time. Okay, so if temp is what? Less than 70, then oh gosh. Print. Too cold. Else if temp is more than 90. Too hot. Else return just right. And I missed a whole load of semicolons. Semicolon. Easy peas. So, ternary. Just like JavaScript, C has a ternary operator. Let's break down the syntax. So that's the condition, and then if it's true, that or that. The entire line is a single expression that evaluates to one value. Here's how it works. A greater than B is the condition. A is the final value if the condition is true. B is the final value if the condition is false. The entire expression evaluates to either A or B, which is then assigned to Max in our example. Ternaries are an easy way to write simple if-else statements in one line. My recommendation, don't use them. Okay, just kidding, they're fine. Just don't use them like a JSND on every single line just to save the 3 keystrokes. I find them most useful when you try and set a single value to the result of some Boolean expression like max in the example above. Generally speaking, I think you're better served with if statements in C. Yeah. What's the result of 1 equals 0, true or false? It's going to be F. False. Type sizes. In C, the size in memory of a type is not guaranteed to be the same on all systems. That's because the size of a type is dependent on the system's architecture. For example, on a 32-bit system, size of an int is usually 4 bytes, while on a 64-bit system, the size of an int is usually 8 bytes. Of course, you never know until you run size of with the compiler you plan on using. However, some types are always guaranteed to be the same. Here's a list of the basic C data types along with their typical sizes in bytes. Note that sizes can vary based on platform. Example, 32-bit versus 64-bit systems. So basic C types and sizes. So char is 1 byte, represents a single character. Notes, always 1 byte, but can be signed or unsigned. Float. Size 4 bytes. Represents single precision floating point number. Double. Size 8 bytes. Represents double precision floating point number. The actual size of these types can be determined using the size of operator in C for a specific platform, which we'll learn about next. The size of a data type in C is the same on every computer. So, size of. C gives us a way to check the size of a type or a variable, size of. You can use size of like a function, although technically it's a unary operator. So, quick look what that means. Unary operator. Unary operator. So, in mathematics, a unary operation is an operation with only one operand, a single input. This in contrast to binary operations, which use 2 operands. For example, an example is any function, where A is a set and function is a unary operation on A. Absolute value. Obtaining absolute value is a value of a number is a unary operation. This function defined as that, blah, blah, blah. Examples from programming languages. So, unary puts, okay. Okay. But that distinction is generally only useful for winning super important internet arguments. We'll use the size of operator in the next few lessons to give us insight into the memory layout of different types in C. This will be particularly useful as we move deeper into C and essential for understanding pointers. Pointers are not too bad once you understand the basics, I promise. So, size T. The size T type is a special type that's guaranteed to be able to represent the size of the largest possible object in the target platform's address space, i.e. can't fit fits any single non-struct value inside of it. It's also the type of size of returns. Size t. The size t type is a special size t is the unsigned integer type of the result of size of offset. Okay. That is guaranteed to be able to represent the size of the largest possible object in the target platform's address space, i.e. can fit any single non-struct value inside of it. It's also the type of that size of returns. So run the function to see the size of char. 1. Update main to also print the size of each of the following types in order, keeping char the first one. So 1, 2, 3, 4, 5. So bool int float double size underscore t, size underscore t. Let's see what it does. Okay, so boolean, char and boolean are both 1 byte each. A float can be, oh wait, sorry. A char and a boolean are 1 byte each. An int is 4 bytes, float is 4 bytes, double is 8, and size t is 4. For loop. So a for loop in C is a control flow statement that for repeated execution of a block of code. Very similar to Python, but with a different syntax. The syntax for loop in C consists of 3 main parts: the initialization, condition, final expression. There is no for each iterables in C. For example, there is no way to do for car in cars, print car. Instead, we have to iterate over the numbers of the indices in a list, and then we can access them, access the item using the index. So for initialization, condition, final expression, loop body. So parts of a for loop: initialization, execute only once at the beginning of the loop. It is typically used to initialize the loop counter, so int I equals 0, for example. Condition, check before each iteration. If true, execute the body. If false, terminate the loop. Often checks to ensure I is less than some value, like I is less than 5, for example. Final expression, executed after each iteration of the loop body. Can be used to update the loop counter or run any other code, I++, for example. Loop body, block of code that is executed. The block code is executed while the condition is true. Example of a basic loop. So it says, assignment implement print numbers, prototyped in exercise.sh. That takes a starting number and ending number and prints all the numbers in that range inclusive using a for loop. So, we don't need the thingy part. And oh, hold on, important lesson thing to be done. Okie dokie, important job of the evening done. if you're still with me, peeps. I hope you're having a good time. It's pretty fun so far. I'm enjoying this. So let's see what comes out with this. Whoops. Whoopsie daisy. Start and end mistyped. Waited 69. Bingo. Oh. It's a little bit stuck. Ta-da! Yay. While loop. So, a while loop in C is a control flow statement that allows code to be executed repeatedly based on a given Boolean true or false condition. The while loop continues to execute as long as the condition remains true. So while, condition, loop of the body. Parts of a while loop. So condition, check before each iteration. If true, execute the body. If false, terminate the loop. Loop body, the block of the code that is executed while the condition is true. Example of a basic loop. So key points, the condition is evaluated before the execution of the loop body. If the condition is false initially, the loop body will never even start. If the condition never becomes false, you'll get an infinite loop. Assignment, implement the print numbers reverse prototyped in exercise H. It takes a starting number higher and an ending number lower and prints all the numbers in that range from the highest to the lowest inclusive. This time use a while loop. So while so I guess while end while a start is greater than end, then I guess keep forgetting the syntax for print, but yeah, printf. I suppose probably not a good idea to do that actually. I guess we say like so I say start underscore decreasing equals start, and then we'll say start underscore decreasing, and then we'll do start decreasing minus minus like that. Do that. What did I forget? Semicolon. Bring from 20 to 4. Greater than or equal to that. Try that way. Yay. Pretty simple. Hey. Do while loop. So a do while loop in C is a control flow statement that allows code to be executed repeatedly based on a given Boolean condition. Unlike while loop, the do while loop checks the condition after executing the loop body. So the loop body is always executed at least once. So do loop body while that. So parts of a do while loop. So the loop body are the block of code that's executed before checking the condition and then repeatedly as long as the condition is true. So condition checked after each iteration. If true, execute the body again. If false, terminate the loop. So examples like, yep, do this while that. Another one, yep. Key points. The do while loop guarantees the loop body is executed at least once, even if the condition is false initially. The most common scenario you'll see a do while loop used in C is in C macros. They let you define a block of code and execute exactly once in a way that is safe across different compilers and ensures that the variables created / referenced within the macro do not leak to the surrounding environment. If you end up looking at any source code for macros, you'll probably see a few do while loops. For example, here's a simplified version from our unit testing library we're using. So unit assert type full do while 0. It creates a do while loop, creates a few new variables and then checks that the assertion is valid. If it is not, then it errors and formats a complicated error message. If this code doesn't make any sense, that's fine too. I just wanted to show you where they most often occur. There is no semicolon after the while 0 in the loop above. This lets the macro be used as a block of code without causing syntax errors. When writing a normal do while loop in your C code, not in a macro, you must include the semicolon after the loop. Assignment. Run the code. Notice that it prints numbers 5 to 1 in decreasing order. However, when the starting number is less than the ending number, it doesn't print anything because the condition of the while loop is never true. Modify the print reverse numbers function to use a do while loop so that it always prints the starting number at least once, even if the condition is initially false. So do this, swap that, so we go do, and then while. Is that the right way? Yep. So do while like that. Run that. We need a semicolon. Is that? Happy days. Pragma once and header guards. We saw how .h header files are used in a previous lesson, but before we go further, let's talk about a potential issue you might run into: multiple inclusions. In the same header file, if the same header file gets included more than once, you can end up with some nasty errors because by redefining things like functions or structs. Pragma once. One simple solution and one we'll use for the rest of this course is hashtag #pragma once. Adding this line to the top of the header file tells the compiler to include the file only once, even if it's referenced multiple times across your program. So my header.h pragma once struct point x and y. Header guards. Another common way to avoid multiple inclusions is with include guards, which use preprocessor directives like this. So if not defined, my header h, define my header h. Some cool code, end if. This method works by defining a unique macro for the header file. If it's already been included, the guard prevents it from being processed again. Throughout this course, you'll see pragma once in our header files. It's quicker and less error prone than traditional include guards, and it works well with most modern compilers. What is the purpose of pragma once in header file? Prevents the header file from being included more than once, avoiding redefinition errors, improves the prompts of the program, it automatically generates function prototypes, it allows the header file to be included multiple times in the same program. The first one. Doop. Nice. So we're in chapter 2, structs. It is 20 to 9. I'm feeling not like totally horrible. So what I think I'm going to do is I'm going to get through this, and then we've got through 2 chapters tonight, then we've got 2 more sessions this week. So I'm thinking let's do structs and pointers, and then what we got 11 take 3 8. So then we got 4 lessons to do in each of the other 2, and then then we'd be happy. And some of these are probably going to take longer than others. So let's see if we can do structs and pointers, and then we'll leave it there for tonight. So structs.
Structs in C are similar to classes or objects in Python or JavaScript, but they are a bit simpler. There aren't any concepts of things like inheritance or class methods or static variables, nothing like that. Instead, structs are simply a way to group multiple fields or data points, so you could sort of think of them out, and put them all into one object, right? So they get to be moved around and stored together. This is really useful because instead of typing 35 separate variables to a function, you can put some of those variables, logically group them into a struct, and pass them around together. This is the same reason why you often would make something like a data class in Python or just a simple object in JavaScript. They are similar to objects as well in that they have a list of fields, but as I mentioned, they don't have any methods. They're only data. They have no behavior. And you can access the fields of a struct with the dot operator, or if you have a pointer to the struct, then you can access them with the arrow operator, which is really a dash and like greater than thing. And if you have ligatures, then it looks cool like a real arrow. That's kind of my preference. But one thing that is different than what you can expect from Python or JavaScript is that the order that you define the fields actually matters in terms of the size and the layout of memory. When we make a struct, what we're really doing is we're telling C, I have several different pieces of data. I'd like you to put them next to each other in memory, and I'd like to operate on that memory as sort of like a block, right? And that block can be bigger or smaller depending on how we lay out the data. Now, in other languages, you don't always have to think about this, but in C, you're tending to write things where you need to really crank out the last bit of performance. Really, everything in C, when we're talking about data, is just a bunch of bytes in a row. And our program is the one instructing the computer how to and where to access those bytes. C is really, in a way, a language of describing data and then what we want to do with that data. It doesn't have other ideas like encapsulation and methods and all of this other stuff that sort of hides away everything that we're doing.
Okay. So far, all we've seen are simple non-collection types in C. However, stuff like this can be really annoying. So x1, y1, z1, x2, blah, 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 blah. Int distance is all of these, and then distance that. So because our distance function starts to look ridiculous, we also run into a new problem. In C, we're only allowed to return a single value from a function. This doesn't work. Too many values to return. Okay, structs solve this. Here's our example syntax. So a human has age, a name, and is alive. So Simon, so Snecklang has built so Snecklang has built-in support for graphics programming and vows to never gouge game devs. Define a new struct called coordinate in coord.h. Remember that H files are for declarations of types and function prototypes. The coordinate struct must have the following 3 fields. So an integer x, an integer y, and then an integer z. Okay. Easy McCheesy. Initializers. So now you're probably wondering, hey TJ, so how do we actually make an instance of a struct? You may have noticed in the previous lesson, all we did was define the struct type. Unfortunately, there are a few different ways to initialize a struct. I'll give you an example of each using this struct. So, struct city, it has a name, a latitude, and a longitude. A 0 initializer. So struct c, city c equals bracket 0. This sets all the fields to 0. Okay. Position initializer. Okay. So you, like, yeah, which one it is in which way. Set the number. Designated initializer. This is generally my preferred way to initialize a struct. Why? It's easy to read, has the field names. If the field names change, you don't have to worry about breaking the ordering. Yeah, I prefer that as well. Remember, it's .name, not name. If this trips you up, remember it's .name and not name because that's how you access the field. C.name. So accessing fields. Accessing a field in a struct is done using the dot operator. For example, struct city c dot lat equals 41. Set the latitude. Print the latitude is like that. So there's another way to do this for pointers, and we'll get to that later. Complete the new coord function. It accepts 3 integers and returns a coordinate. Use the designated initializer syntax because I said so. Fair enough, teach. So we're going to say return struct city, is it? Or is it coordinate? Excuse me. Struct coordinate and then I guess coord do I have to put that? Will it just be like that? And then x, sorry, it's dot x equals x, and then dot y equals y, and then dot z equals z. We have to have a comma between all that. Not the last one though, and let's just see what it does. Expected expression. Guess you can't just like return it, so whoops. Semicolon. Okay. Pretty simple. Let's see if they did a one-liner, because I'm always curious. Yep. Well, actually, no, they didn't do a one-liner. They just did the same thing. Coord equals that. Yeah, it's pretty much the same. So scaling coordinate. Remember how we cannot return multiple values from a function in C? We can't do this. However, we can accomplish effectively the same thing by returning a struct. So open quad .h, add a declaration for the scale coordinate function as defined in the coord.c file. Scale coordinates. Complete the scale coordinate function in coord.c. It should return a new coordinate where each field is scaled up multiplied by the factor parameter. Okay, so struct, it should return coordinate, coord equals I forget the thing again now, the designated syntax. Oh no, it's just like this. So then it'll be and what was it? Each field is scaled up by the multiple. So x equals so say scaled quad, return scaled quad, semicolon, quad dot x multiplied by a factor, like that. And then it's going to be the same, but just with like, so y, z. Variable has incomplete type struct quad. Whoopsie daisy, spell it wrong. Happy? Yes, happy. Yay! Type def. By now you're probably tired of typing struct coordinate over and over again, and you're wondering, how can I make my struct types easy to write like int? Good news, C can do this with type def keyword. So struct pastry blah blah blah. This can also be written as type def struct pastry, like that. Now you can use pastry tree wherever you want to use struct pastry. The underscore t at the end is a common convention to indicate a type. In fact, you can optionally skip giving the struct a name. In this case, you'd only be able to refer to the type as pastry t. In general, I do give the struct an actual name, e.g. pastry, but I only use type def type. We'll be using this convention in this course. So update the coordinate declaration in coordinate.h to use the typed def to create a new type called coordinate underscore t. So it'll be typed type def, like that. Update the new quad in scale coordinates function to use coordinate t instead of type struct, like that. Okay. Like that. Yeah, it's just the same. Nice. Okay, size of. As we saw earlier, size of can be used to view the size of a type. For once, programmers thought of a name that was actually helpful. But this isn't just true of built-in types like int or float. You can also use it to find out the size of structs. So print size of coordinate t, zu bytes, and then size of coordinate t. Memory layout. So structs are stored contiguously in memory, one field after another. Is that supposed to be contiguously or continuously? Contiguously. Oh, continuous. Okay. Take this struct. That. Assuming int is 4 bytes, the memory layout for coordinate t would look like this. So field x, field y, field z. Okay. So then mixed type struct. So char, int, and double. Assuming char is 1 byte, int is 4, and double is 8. The memory layout for human t might look like this. So first initial padding, age, and then height. Assuming char is wait, what is that padding doing there? It turns out that CPUs don't like accessing data that isn't aligned. Incredibly oversimplification alert, but since obviously CPUs don't have feelings yet. So C inserts padding to maintain alignment, e.g. every 4 bytes in this example. Huge caveat, these layouts can vary depending on the compiler and system architecture. So size of struct will always result in the same value as the sum of size of field for each struct. False. Because size of first initial would be 1, but the overall struct gets the padding basically. So struct padding, last one in structs. So struct padding. There are a bunch of complicated rules and heuristics that different compilers use to determine how to lay out your structs. But to oversimplify, the field of a struct are laid out in memory contiguously next to each other. Structs can vary in size depending on how they are laid out. C is a language that aims to give tight control over memory. So the fact that you can control the layout of your structs is a feature, not a bug. Compilers plus modern hardware plus optimization plus skill issues means that sometimes what you think the computer is going to do isn't exactly what it actually does. That said, C is designed to get you close to the machine and allows you to dig in and figure out what's going on if you want to for a specific compiler architecture. As a rule of thumb, ordering your fields from largest to smallest will help the compiler minimize padding. So assignment, rearrange the fields in SNEC-lang-var-t so that padding is optimal in the tests in main.c pass. So I guess largest to smallest. So I guess it's going to be ints first, then I guess character strings are the longest, like that, because they're 4 as well. I wonder if there's only one right example. Yeah. Okay. Right, so we're at 9 o'clock. It's pointers. What is an address virtual memory? Let's see how far we do. Let's get to past and then probably call it quits for tonight. Yeah, because then we got a straight run at things like 1, 2, 3, 4. 1, 2, 3, 4. Yeah. We get 3. If we get 3 done, chapter 3 done, that'd be great. Because then we got 2 sets of 4 to end the week, and then we get this course done in 1 week. That'd be amazing. But we'll see. We'll see if we get through it that fast. Memory. So before we talk about pointers, we should talk about variables and memory in general. Here are some useful, albeit hand-wavy mental models. Variables are human-readable names that refer to some data in memory. Memory is a big array of bytes, and data is stored in the array. A variable is a human-readable name that refers to an address in memory, which is an index into the big array of bytes. Here's a diagram. So the variable name, name, handle, value is tej_dev, address is 0, address is 4, size is 4 bytes, size is 8 bytes. Starts at 0, fills 4, starts at 4, fills 8. Getting a variable's address. In C, you can print the address of a variable by using the address of operator. Ampersand, here's an example. Include standard input output.h. So then you can do using the address of operator. Okay, like that. Address of is x. Oh, okay. So the %p format specifier will format a pointer memory address to be printed. Assignment: the size of address function accepts a long. a potentially very large integer, as input and returns the size of its address. There's a bug. Memory addresses in SNEClang should always be 4 bytes long. Fix the function so it returns the size of i's address, not the value. Like that. Memory addresses in SNEClang should always be 4 bytes long. Fix the function so it returns i's address, not the value. So what is an address? So I mentioned in the last lesson that memory can be thought of as a big array of bytes, and each byte has an address. That's true, and the beauty is that each address is literally just a number. It's not some mortal address like 1234 Elm Street or 1600 Pennsylvania Avenue. It's just a number. You might be thinking, hey, if it's just a number, why does it look all disgusting like 0xFFF8? That's because 0xFFF8 is just a number, but it's written in hexadecimal base 16 instead of decimal base 10. It's a pretty big number, so it's not very human readable. 0xFFF8 is the same as 65,528 in decimal. Green is hexadecimal, blue is decimal. 408, 409, 40A, 40B, 40C, okay. Which looks the most like memory addresses? 11Cs. Take the second circuit past the transistor, then a hard left. 22 1 Baker Street, London. That one. Virtual memory. So as it turns out, your code probably doesn't have direct access to the physical RAM in your computer. Instead, your operating system provides a layer of abstraction called virtual memory. Virtual memory makes it seem like your program has direct access to all the memory on the machine, even if it doesn't. So physical memory, the actual RAM sticks in your computer. Operating system, the software that manages access to the physical memory. Your program, when it runs, it becomes a process and is given access to a chunk of virtual memory by the operating system. Your program, when it runs, it becomes a process and is given access to a chunk of virtual memory by the operating system. Virtual memory, this abstracted chunk of memory that your program can use. There are exceptions to this. For example, if you're using C to build embedded firmware that runs without an operating system, your code might interact directly with physical memory. So, program has memory to the operating system. Looks at the physical memory. Knock yourself out. Virtual memory. By only giving processes accesses to a chunk of virtual memory, the operating system can do some cool things. Isolation. One process can't access the memory of another process. Security. The operating system can prevent processes from accessing certain parts of memory. Simplicity. Developers don't have to worry about managing physical memory and the memory of other processes. Performance. The operating system can optimize memory access depending on the hardware needs of the program. For example, by moving data between physical memory and the hard drive. At the end of the day, your program has direct access to a virtual chunk of memory, just like physical memory. It can be thought of as a big array of bytes where each byte has an address. So the memory addresses that your code sees are the same as the physical addresses in the RAM. Never most likely not because the operating system provides a virtual address space. Most likely because the operating system, always that one. Pointers. Oh, you've probably heard of pointers. You may have also seen jokes about how they're impossible to learn. Well, that's wrong. In fact, now that you understand how memory is laid out in an array, a lot of the mystery behind pointers should be gone. Put simply, a pointer is just a variable that stores a memory address. It's called a pointer because it points to the address of a variable which stores the actual data held in the variable. So let's have a listen to the video.
Pointers. Anyone who tells you that they're very hard has skill issues. We're going to walk through why. We need to remember here is that pointers are actually just a value that tells you the address of another value. Consider int x equals 5. In this simple statement, what we're going to start with here is that we have some variable x, and it's going to have some address in memory. We're going to just make one up, okay? It's not a huge deal. But what we're going to show throughout this section is think of pointers as just addresses, the data, and you're going to be all right. We start with our first one, x. We give it some long, big address, which is similar to the thing you'll see printed out when you print out pointers in these lessons. And then we give it a value, like 5. Now, when we create another value, like y, and we say that is equal to x, what we're actually doing is copying the data of what was ever at x and putting that into y. Remember, this is a copy. So, if we do something like update the value of x, what's going to happen to the value of y? Nothing, okay? Instead, what we'll have is only x will get updated. Now, here's where we're going to start introducing pointers. We introduce this by saying int star and then a name. So this is saying the type of this is a pointer to integers, and we're going to point it to the address of x. We do that with a fancy ampersand. So what we have, though, is this pointer, and it's at some other address in memory, but its value is actually that original address of x that we're talking about. You should just think in your brain, what we're doing is I'm setting that value to here. We've copied the value of the address. This is like if I give you my address is 1234 Sesame Street, we're going to copy that in. Now, when we do something like dereference that pointer, which is saying, hey, I'd like to get the value out of that pointer, and we set it into z, we create a new name and a new address, and we set that to a new value. Once again, very important, this is a copy operation. Okay, this means that we cannot just say that these things are going to be in sync forever, but instead that it is a copy. Just the same as when we copied the value from x into y. However, now what's going to happen is if we say, hey, let's change what's in the memory location that the pointer points to. Well, we go back to our table and we refer there and we say, aha, I need to update my value of x. So what we have is still just copying values into new locations in memory. It's just that sometimes the value itself is an address.
Yeah. So that sounds simple enough. So syntax: a pointer is declared with an asterisk after the type. For example, int asterisk. Remember to get the address of a variable so that we can remember to get the address of a variable so we can store it. It's in a pointer variable. We can use the address of operator. So like that. Learning about pointers is nearly impossible. Easy when TJ writes the course material. A waste of time, just write Python. Why pointers? So to illustrate the usefulness of pointers, let's pretend we want to pass a collection of data into a function. Within that function, to illustrate the usefulness of pointers, let's pretend we want to pass a collection of data into a function. Within that function, we want to modify the data. In Python, we could use a class to store the data, a pass an instance. In Python, we could use a class to store the data and pass an instance of the class into the function. So there's the class, update coordinate x, you give it a coordinate, new coordinate x equals new x. C equals new coordinate, 1, 2, 3. Print c.x is 1. Update coordinate c to 4. Print c.x is now 4. Now let's do the same thing but using a struct in C. complete the coordinate update x and coordinate update and return x. Coordinate update x should update the x field with the provided new value. It returns void. Okay, I guess so. Return coord. What is it? Coord.x equals new underscore x. Coordinate update and return x. Should update x field with the provided new value and return the updated coordinate structure. Okay, so then it's going to be and then I guess return coord. Remember, you can access a field of a structure using dot operator like so. What happened after passing the assignment? Open up main C and take a look at the test cases. You'll notice that coordinate update x doesn't update anything, but coordinate update and return x. Whoops. Assertion failed. X must be 4. Let's do that, void. No? What happened after passing the assignment? Open up the main C file and take a look at the test case. You notice that the coordinate update X doesn't return anything, but the coordinates it does because it returns a new copy of the structure. In C, structs are passed by value. That's why updating a field in struct in the struct does not change the original struct from the main function. To get the change to persist, we need to return the updated struct from the function, a new copy. The memory address of the struct that went into the coordinate update and return X was not the same as the address of the struct that was returned, again because we created a copy. Okay. So pointer basics. How many have we got? 17, gosh. Remember, pointers are just an address, read value, that tells the computer where to look for other values. Just like how the address to your house is not actually your house, but points you to where your house is. So syntax review. Declare a pointer to an integer. Okay, declares pointer to something as a pointer to an integer. Get the address of a variable. So, okay, pointer to mall now holds the address of meaning of life. Remember, pointers are just an address read value that tells the computer where to look for other values. Just like how the address to your house is not actually a house, but points you to where your house is. So new dereferencing pointers. Oftentimes we have a pointer. We want to get access to the data that it points to, not the address itself, but the value stored at that address. We can use asterisks to do it, and the asterisk operator dereferences the pointer. So this is a pointer, points to the address of that, and then this is the actual value of that. It can be a touch confusing, but remember that the asterisk symbol is used for two different things: declaring a pointer type, dereferencing a pointer value, retrieving the value, or modifying the value. Okay. Assignment. So fix the change file type. Accept a pointer to a code file. So guess that. Dereference the pointer to a code file T struct. Change the file type field fix both there. Okay. Dereference the pointer into a code file T struct. Change the file type field to the provided new file type value. Return the updated code T struct. Accept it pointed to a code file reference. Dereference the pointer to code file T struct. Change the file type field to the provided new file type value. Return the updated file type T struct. Okay. I got it, but Boots, can you explain this? Accept a pointer, dereference the pointer into the code file struct. I was already there. Change the file type field to the provided new field file type, yeah. And then return the code file struct, new file. Okay, well, we did it. Pointers to structs. As you know, when you have a struct, you can access the fields with the dot operation, like that. However, when you're working with a pointer to a struct, you need to use the arrow operator. Okay. It effectively dereferences the pointer and accesses the field in one step. To be fair, you can also use the dereference and dot operator to achieve the same result. It's just more verbose and less common. Yeah. Order of operations. So the dot operator has a higher precedence than the asterisk operator. So parentheses are necessary when using asterisks to dereference a pointer before accessing a member, which is another reason why the arrow operator is so much more common. Which of these options is not equivalent? So C arrays. If you're used to lists in Python, arrays in C are similar but a bit lower level. An array is a fixed size ordered collection of elements. Like Python, lists are indexed by integers starting at 0. Unlike Python lists, you can only hold elements of the same type. They are stored in contiguous memory like structs. They only hold elements of the same type. They are stored in contiguous memory like structs. So integer array. So int numbers 5. Iterating over array. So that's what an integer array looks like. Integer numbers, and then 5 is the length. Iterating over an array. So in C there is no for x in list syntax. Instead, you must iterate over them using for loop with an index or some other conditional loop. Yeah. Updating values in an array. So the syntax for updating values in an array is the same as how you would access them. So array index equals value, using our numbers example. Update some values, printed updated array, output is that. Assignment, complete the update file function. The file data array is a large 200 integer array representing a SNClang source file. Each integer in the array represents a special piece of data. Index 1 is the number of lines. Index 2 is the file type. Index 199 is always 0. Update the function so that it overwrites indexes 1 and 2 with the provided values. Okay, so I guess file data, file data 0 equals new num lines. File data 1 equals new file type, new underscore file type. Index 199 is always 0. File data, data 200 equals, I'll tell you what, 1 to 199 is always 0 equals 0. Ta-da! Arrays as pointers in C. So in C, arrays and pointers are closely related. An array name acts as a pointer for the first element of the array. That means that array indexing and pointer arithmetic can be used interchangeably to access array elements. Let's go through this step by step to understand how this works. So, step by step walkthrough. Array declaration. So, int numbers 5 is 1, 2, 3, 4, 5. Here, numbers is an array of 5 integers. Array as pointer. So the name numbers acts as a pointer to the first element of the array. The name numbers acts as a pointer to the first element of the array. Okay. So that's a pointer to numbers. Okay. Numbers PTR is a pointer to the same place as numbers. Accessing elements via indexing. So access the third element, index 2. Int value equals numbers 2, which is the same as okay, pointer 2, okay. Here, numbers plus 2 computes the address of the third element, and asterisk dereference it to get the value. Pointer arithmetic. When you add an integer to a pointer, the resulting pointer is offset by the integer times the size of the data type. So P points to the third element, and then value is 3. Diagram explanation. Let's assume numbers is stored starting at memory address 0x1000. An integer is typically 4 bytes in C. Here's how the array elements are laid out in memory. So number 0 is 1, numbers 1 is 2, numbers 2 is 3, numbers 3 is 4, number 5 is 5. And it goes up in bytes. So like, no bytes, then 4 bytes along, another 4 bytes along, then 4 bytes along, another 4 bytes along. Okay. Accessing elements using pointers. So numbers plus 0 or ampersand numbers 0 points to that. Numbers plus 1, like that, using pointers. So example code. So int numbers 5 is 1, 2, 3, 4, 5. Accessing elements using the array indexing. So the second in the index is going to be 3. Accessing elements using pointers. So numbers, so the first one in the index plus 2. And dereference to get the value of it is 3. Pointer arithmetic. So int, and then we get the is a pointer to numbers, so the first in the sequence. So the first one's going to be 1, and then we plus 2 to that address, and then we dereference it and get the value is 3. Which two statements are the same? Array 4 is plus 4, that one. Yep. Multi-byte arrays. If we create an array of structs, it gets crazy because we can access and manipulate the elements using either indexing or pointer arithmetic. Let's see how multi-byte width structures are managed in memory. First, let's say we're working with our familiar coordinate struct. We can declare an array of 3 coordinate structs like so. Then we can print out the values of the second element in the array. Yeah, it's kind of nice. Or we can use a pointer. So pointer to the first points, and then pointer plus 1. That. We don't have to dereference it then. Memory layout. So assuming each int is 4 bytes, the coordinate structure will be 12 bytes, so 3 times 4 bytes. Let's assume the points array starts at memory addresses 0x like that. Yep. Assume the points array starts at the memory address like that. So here's the memory layout. Yep, makes sense. Access the elements using pointers. So points plus 0 and points to that address. Points to the next struct offset by 12 bytes. Points to that. A struct stores 8 integers in its ordered fields, A through H. An array stores an array stores 10 of these structs. What will the offset in bytes from the start of the array to the 5th element's C field? A struct stores 8 integers in its ordered fields, A through H. So A through H. An array stores 10 of these structs. What will the offset in bytes from the start of the array to the 5th element's C field? So each struct is going to be 8 times 4 is 8 times 4 is 32. 32 times 2. Hold on, 32 times 2, 64. And then it's going to be 64, 74, 80, 82. I got it completely wrong. Hold on. A struct stores 8 integers in its ordered fields, so it's going to be 8 times 4, yeah? So 4 times 8 is 32, yeah? 4 times 8, 32. 32 times 5. 32 times 4 is 64, 128. And then C, 128. 128, 132, 136. Got it. God, need some mathematics in this brain. Array casting. So let's explore a special kind of psychopathy that's possible in C. Let's assume that we have this array of 3 structs where each struct holds 3 integers. Because arrays are basically just pointers, in most cases more on that later, and we know that structs are contiguous in memory, we can cast the arrays of structs to an array of integers. So int point start equals an array of integers for points. Then we can iterate over the known number of integers in the array of structs. Okay. Take a look at the dump graphics function. It works similarly to the example above. Go ahead and run it in its current state. You should notice that after all the values specified in main C are printed, all hell breaks loose. That's because we ventured out of the bounds of our array. We're going rogue. We're in the weeds. We're in undefined territory. This is something you do not want to do. It's one of the things that makes C powerful but dangerous. Other languages stop you from going out of bounds, but C will let you fly off the edge of the world. Fix the loop to only print the values that are actually in the array of structs. Take a look at the graphics T struct in exercise H to figure out how large each struct is. So 4, 8, 12, 12 times 10. 12 times 10 is 120. Oh no, sorry, it's an int, isn't it? So it's going to be 1, right? So 3 times 10 is 30, right? Whoops. Yay. Let's go to the next thing, but let's just refresh because thing had a bit of a moment then. Now, how many lessons we got left? We're on 12. We got to get 17. We can do this. So pointer size. The size of an array depends on both the number of elements and the size of each element. An array is a contiguous block of memory where each element has a specific type. And therefore a specific size. In C, pointers are always the same size because they just represent memory addresses. The size of a pointer is determined by the architecture system, e.g. 32-bit or 64-bit. A pointer size doesn't depend on the type of data it points to, it just holds the address of a memory location. A pointer size doesn't depend on the type of data it points to, it just holds the address of a memory location. Pointer example. 4 bytes, 4 bytes, 4 bytes. Size of int. They're all the same size because they're all just 32-bit memory addresses. It doesn't matter how much memory the value at that address takes up. Array example, so int array 10. Char double, okay. Yep. Now the sizes are different because the array type keeps track of the size of each element and the number of elements. Although an array is a pointer to the first element, it's not just a pointer, it's a block of memory that holds all the elements. Boot.dev runs C in the browser using WASM, which is typically a 32-bit system. If you run this code on a 64-bit system, the size of the pointers will be 8. Blank have the same size on the same system, while blank may have different sizes. Pointers have the same size on the same system, while arrays may have different sizes. No, that's not right. Pointers may have different sizes. No. Pointers have the same size on the pointers have the same size on the same system, while arrays may have different sizes. Yep. Sorry, that was right. Arrays decay to pointers. So now, so we know that arrays arrays are like pointers, but they're not exactly the same. Arrays allocate memory for all their elements, whereas pointers just hold the address of a memory location. Arrays are like pointers, but they're not exactly the same. Arrays allocate memory for all their elements, whereas pointers just hold the address of a memory location. In many contexts, arrays decay to pointers, meaning the array name just becomes just another pointer to the first element of the array. So when arrays decay when used in expressions containing pointers. Arrays decay to int. Arrays decays to int. I get that fly. When expressions contain arrays allocate memory for all their elements, whereas pointers just hold the address of a memory location. In many contexts, arrays decay to pointers, meaning the array name becomes just a pointer to the first element of the array. And also when they're passed to functions, they usually decay quite often in practice. That's because that's why you can't pass an array to a function by value like you do with a struct. Instead, the array decays to a pointer. When arrays don't decay, so size of operator returns the size of the entire array, so size of array, not just the size of a pointer. And ampersand operator, taking the address of an array with and array gives you a pointer to the whole array, not just the first element. The type of is a pointer to the array type. Int asterisk 5 for an int with 5 for an int array with 5 elements. Initialization: when an array is declared initialized, is fully allocated in memory and does not decay to a pointer. Assignment: take a look at the main function. It declares an array of numbers, core utilization, that represents the CPU utilization of each core on a system running a SNEClang interpreter. The array has 8 elements. On lines 12 and 13, it prints the size of the array and the length of the array. Complete the core utils function to print size of core utilization in core utils funcs. X is the size of the array calculated by the size of operator. So I guess print f. It's going to be like that, and then it's going to be size of operator. I've forgotten the thing. It's going to be ZU, isn't it? ZU. Once you complete the function, run it and take a look at the output, you'll notice that due to this, the array decaying to a pointer, the reported size is the size of the pointer, not the size of the actual array. All right. So once you complete the function, Run it and take a look at the output. You notice that due to the array, the provided size of the size of point is not the size of the actual array. Utilization 32, cause utilization 8. Okay. Yeah, it decays because it's passed through a function. So C strings. Since C string library, forward decoration, mutual structs. Okay, almost there. Almost done for tonight. So, since the beginning of the course, we've been doing these since the beginning of the course, we've been doing these shenanigans to be able to print strings. I told you not to worry about the weird char syntax, but now that we understand a bit about pointers, let's dive into it. In the example above, message is a pointer to the first message is a pointer to the first character in the string, blah blah blah, which is a C string. C strings are how I represent text in C program. I'm going to get that at some point. How I represent text in C programs, any number of characters, chars terminated by a null character /0 or /0, sorry. A pointer to the first element of a character array. It's important to understand that most string manipulation in C is done using pointers to move around the array, and the null terminator is critical for determining the end of the string. In the example above, the string ssh terminal.shop for the best coffee is stored in memory as an array of characters, and the null terminator /0 is automatically added to the end. So C strings are simple. Unlike other programming languages, C strings do not store their length. The length of a C string is determined by the position of the null terminator, so /0. Functions like stru length calculate the length of a string by iterating through the characters until the null terminator is encountered. This lack of length storage requires careful management to avoid issues such as buffer overflows and off by one errors during string operations. So pointers versus arrays. You can declare strings in C using either arrays or pointers. Oh, okay. Same thing. The output is the same. Let's break down the memory of this example. Notice we aren't using all 50 characters. So first 50 is snack, and then that one, second one is lang, string cat first and second, and then printf first hello snacklang. The str_cat function appends its second argument to the first argument. In this case, it appends lang to snack, resulting in the output hello snacklang. Here's what first might look like in memory. The /0 is a slash followed by a number 0. Do not confuse it with the O letter. So snack. Yeah, okay. Note there is a bunch of garbage memory after the end of the string. Here's what the second might look like in memory, so lang. And first after stir cat, snack lang, and then a bunch of crap. Stircat function appends the lang exclamation mark to the end of the string snack, but smartly uses the null terminator to know where to start appending. It doesn't know the length of the string, but it knows where it ends. Assignment. So snacklang, we have a bit of a not invented here culture, such as we've decided to implement our own string concatenation function, complete with concat strings function. It should append string 2 to the end of string 1 in place. Here are the steps. Find the null terminator \0 in string 1. Iterate over string 2 and copy each character into the memory locations. Don't treat and use stircat. Okay. Use a while loop and a pointer dereference to see when you reach a null terminator. Increment your pointer with the ++ operator to move to the next character. So I guess it'll be str1 pointer. So I guess we do that. So str1 and then str1 and so pointer is equal to /0. Then what do we do? Iterate over, so find the null terminator, iterate over string 2 and copy each character. Iterate over string 2 and copy each character into the memory locations at the end of string 1. Add a null terminator to the end of concatenate string. Oh gosh. Might have to come back tomorrow for this one. My word. Right, so I think I got that. So like find the null terminator in whoops. Well, we're not done yet. We will wrap up in a minute though. uh okay, iterate over string 2 and copy each character into the memory locations at the end of string 1. So in string 2 length equals string length and string 2. Then I guess I do traditional like 4, so 4. Add an alternate to the end of the concatenated string. So I guess 4 int I equals 0, whilst I is less than string 2 length. I plus plus. Okay. Got loads of missing semicolons, just realised. So then we do then we do string length terminator plus string 2 underscore length. And then /0, something like that. Or do I have to import this string length thing? Unspecified when result comparison against a string literal is unspecified. Is that the doozy? I guess print f. What's the problem here? So, result of comparison string against the literal is unspecified. Use explicit string comparison function instead. Increment your pointer with the plus plus operator to move to the next character. Copy character by dereferencing and assigning the value of one pointer to another. Well, I'm going to need Boot's help at this point. It's been a while. What am I doing wrong? Yeah, just give him the fish. And I spotted classic C trickiness now that you're using. Oh no, it's not double quotes versus singles. In C is a string literal an array of any characters, but is a character literal. Oh no, it's not that. I thought I was being sensible. I thought I was being a good citizen. This just fixed everything that I was doing. Oh, no way I had to use boots and all I had was that. Okay. Blah, blah, blah. Here's some questions to guide you your while loop. What type is it expecting a character or a string? When you assign blah, 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 what type is being assigned? Should it be a string or a single character? You need to include string H if you are not allowed to use string cat. I need string length, don't I? Right, let's see what I got it anyway. Let's see what they did. So character end. So pointer to string 1. The position of string 1, okay? So while end is not equal to 0 plus end. Okay, right, okay. And then while string 2, the pointer to string 2's value is not the null terminator, then end is string 2 plus end. Right, okay, that was really simple then. Okay, I need to better understand the pointers in this. Oh god. Righty ho. I think we're going to call it F for tonight because I'm looking at this and I'm thinking, nope. Brain is like, nope. And we will finish it off tomorrow. So yes, I'm going to run away. Tonight's been fun. Very fun. I have not done C before. It's opened my eyes. And it is very interesting and very doable for a lot of people who probably, like me, think they're kind of like too dumb to do it, but you can. I've done some now. I'm getting used to it. I'm enjoying it, and I will be doing more. But anyway, that'll be it for tonight. Thanks for coming down and watching. Hope you had fun. If you're coming in from the future, let us know where you got that time machine. Have a good night. Stay rested. Sleep well. And I'll see you next time.